Hi, welcome to the Signal Path. In this episode, I want to show you a module which you probably haven't seen before. This is an Agilent 86109B. This module is a little bit old. The current state-of-the-art one is an Agilent 86109C, and that one costs about $85,000. So this is a really expensive module, and this is part of a DCA mainframe, which is a subsampling oscilloscope, and I'll talk about that. And this thing actually is capable of receiving up to 40 gigabit per second from an optical input and up to 50 gigahertz of analog bandwidth from its electrical input. So it's an oscilloscope. The DCA is an oscilloscope. It's just a subsampling oscilloscope. And as you can see, this is a dual optical electrical module used for optical communication testing and so on. And if you're in that business, I'm sure you've seen them. So the question is, well, how the heck does this thing do 50 gigahertz of analog bandwidth? How can I sample 50 gigahertz of analog bandwidth in such a form factor? And how does the actual DCA mainframe work? Well, before we take this apart and take a look at what's going on and what's inside it, this is a broken unit. Obviously, you can tell from that big X-ray drawn on it. I want to tell you the difference between a subsampling oscilloscope and a regular real-time oscilloscope. And once we understand it, then it will be much easier to understand the components that we will find once we take this one apart. So let's get started. So before we can talk about how this subsampling oscilloscope works, let's just go over how a regular, traditional, real-time sampling oscilloscope operates. Now I'm sure you're familiar with this and you've seen this before. Imagine you have an input signal and you're interested in digitizing it with sufficient signal integrity and sufficient bandwidth to have a good reconstruction in the digital domain. And in the digital domain, then you can either display it on the oscilloscope screen or actually perform FFTs and DFTs and get spectral content or do some DSP on it. And in order to do that, you have to make sure that you sample the signal based on the Nyquist criteria fast enough to avoid aliasing. And not only that, if you want to have sufficient signal integrity, you need to sample it much higher than the Nyquist criteria. And traditionally and typically up to a factor of 10 even factor of 20 in order to be able to get a good signal. So let's say you have a 100 megahertz oscilloscope, you typically find a 1 gigasample per second or a 5 gigasample per second A to D converter that will digitize that 100 megahertz signal for you. But now if your input signal is sitting at tens of gigahertz, this sample clock that samples the signal has to now be in the hundreds of gigahertz. And the trigger signal has to be exceptionally fast in order to be able to catch the transition in the input signal you're actually interested in seeing. Now this becomes an impossible problem when your input signal is sitting at 100 gigahertz. But well, I shouldn't say impossible, because nowadays you have 80, 90, 100 gigasample per second A to D converters, and that's going to continue to improve. But those are the highest cost solutions you can find in order to digitize a signal with A to D converters that have hundreds of gigasample per second sampling rate. So a much simpler solution can be found if you give up on having a real-time sampling and perform subsampling. And that's how this instrument works. And as soon as you limit yourself to a subsampling system, you have to limit your input data to be periodic. If your input signal is not periodic, then you cannot do a subsampling architecture and reconstruct your waveform. So how does the subsampling work? Well, imagine I want to reproduce a square wave, but I cannot sample this square wave at its Nyquist criteria. Let's say this signal is sitting at 50 gigahertz. I cannot sample it at least 100 gigasamples per second. But what I can do is I can sample it even at 10,000 samples per second or 50,000 samples per second, which is what the DSA oscilloscopes from Keysight actually do. And what they do is that they have a trigger that's running in the background, and once every 50,000 of a second or so, it samples the input signal. And then it waits many cycles of the input signal before it samples the next one. But the key is, each time it advances the sampling point by a tiny fraction of time. And that tiny fraction of time has to be exceptionally precise. Otherwise, you won't be able to reconstruct the signal. So it takes a sample from here, then waits a whole bunch of time, then it takes a sample again, which is a tiny bit later than the old one, and then it puts it back onto a buffer, and then eventually it will be able to reconstruct the input waveform. Now, there's also another trick here. You have to make sure that the clock for the trigger circuitry is synchronous and coherent and locked to the input signal frequency. Otherwise, you also cannot do this. So this makes the setup quite a bit more complicated, because now not only do you have to have a synchronous clock available, you also have to have your input signal be periodic. But the trick is that the instrument ensures that this step in time is extremely precise. I mean, you can look at it here. It's that incident where we're trying to digitize the rise time of this waveform over here. First time you're waiting 24 nanoseconds. The second time you wait 24.001 nanoseconds. So there's a tiny step in time. And each time you can see it goes up by 0.001 nanoseconds, so a picosecond, so tiny steps in time. And this is very important, and it's not easy to be able to produce a signal that has such a precise step transitions in it. And that's the whole idea behind the real-time versus the subsampling oscilloscope architecture. And if your signal is non-periodic, for example, like this one, I should say non-monotonic like this one, but it is periodic, then you can still reconstruct it and produce an eye diagram like this one. You will sample it here, then many bits come through. Next time you will sample it here, and that's going to put it right there. And it's going to continue to do this, and you're going to eventually end up with an eye diagram. But this input signal data has to be periodic eventually in order for you to be able to get this eye diagram. And its frequency of periodicity should be synchronous and coherent to the trigger frequency. Otherwise, you cannot do it. So that's kind of the architecture of how this thing works internally, and that's why you're able to get yourself a signal and digitize a signal that has frequency content in the tens and tens of gigahertz, because it doesn't matter, your ADC is running at a much lower rate at tens or hundreds of kilohertz, but at very precise timing. Now, having said that, there is other advantages to this. You can now build your A to D converter to have ultra high resolution. It can be 16 bits, it can be 18 bits, because it doesn't have to deal with a very fast clock. So its resolution is really high. And that would mean that its noise is very low. So you can have very good signal integrity in this architecture, but not sample signals that are not periodic. So you get bandwidth, signal integrity, but none has to be periodic. And that's the key. And of course, this becomes slower in terms of the data being captured and so on, because you're not capturing in real time. So if you have little events in between, you will completely and utterly miss those events. But that's the price to pay in order to be able to do all the other things this provides. So what does a block diagram of a system like this look like? Well, here's the receiver module. This is what we're going to take apart. This is what we're going to take a look at. And it's obviously going to need a sampler in the front end, because the signal coming in is broadband, so you need to sample it, and that sampler has to have extremely high bandwidth at its input, up to 90 or 80 or 50 gigahertz depending on the module input. But then after it has this pulse sampling applied to it, then it now has very low bandwidth because it's already gone through the sampling process, and then all you need is an IF amplifier here, and then the A to D converter, the memory, all the other memory sequencers and all that, the delay trigger generator, all of that is in the main frame of the oscilloscope itself, which I don't have one here. And there is an entire precision time-based module here with an external time that comes in, which then coherently synchronizes this whole system together. Remember that this frequency coming in and the channel input frequency have to be synchronous, otherwise this whole thing would fall apart. So this sampler is like a down convert mixer in a way. That's why they call this an IF amplifier, because you're really down converting the signal and filtering it in a very narrow band. But then because it's periodic, you're using that periodicity. Remember, periodic signals in the frequency domain have discrete frequency content, and that's the trick of getting this to work. If you don't have that, you cannot do this. So we're going to take this apart, and I'm looking forward to seeing, and this one has an optical input, so I'm looking forward to seeing the optical photodetector. We can take that apart, looking at the sampler, take that apart. These are all custom modules made by Keysight or other companies, and we're going to be able to take a quick look at them and see what they've built here. So it should be pretty exciting, and I hope that you learn the difference between these two types of systems and how they can be applied in a different situation depending on what it is that you're trying to test. Alright, now that we understand how this subsampling oscilloscope actually works and what components to expect in the module here, we can take it apart and take a look inside. Now, I don't think I went through it carefully enough in the front. Just to show you again, we have our analog input 50 gigahertz bandwidth, optically modulated 50 gigahertz bandwidth. There's a probe power at the front, which you can use, for external probes and so on. And then you have, vertical adjustments, just like you would have on a regular oscilloscope. So this is like channel 1, this is like channel 2 of a traditional oscilloscope. So there's no difference from that perspective. And at the back here is the interface to the DCA mainframe itself. And you can see that there are many empty connectors here. That's because this shape, this chassis, is for all the different modules. So depending on module, this will be populated differently. In this case, there isn't really much to send back to the oscilloscope. There is a parallel interface for power and low frequency stuff, and there is one analog RF interface, which is a coax cable gets plugged into the back of the DCA, and I'm not going to tell you what that is yet, so you can think about it as we go forward. But since you know the architecture, you should be able to guess what that is for. So let me show you the other side. On this side, we have nothing more than just a PCB with a bunch of passives, and the exciting stuff is all over here. So let's take a look, and based on what we've just went over, we should be able to reason out exactly what it is that we're looking for. So let's follow the signal path, pun intended again. So here at the very top, we have our optical input. So the optics, the light comes through here, which is modulated, and underneath it, right down in there, is the 50 gigahertz analog input. And that one is connected to this over here. So we have our analog 50 gig input, we have our fiber coming in, and this yellow cable is a fiber optic cable. And if you follow that, you can see that it goes into this module, and this module is a photodetector, so it does optical to electrical conversion, and the signal coming out of here is a direct detected signal based on the optics input, and this is also an electrical signal now, which is very similar to the signal over here. So this is after optical conversion to electrical. Here we have two very high frequency analog inputs from channel 1 and channel 2 after this conversion has happened. And no surprise, they both go to an identical block here. So what is this block? Well, if you remember, this has to be our sampler, because the frequency content of these signals is still very, very high. This is our full bandwidth 50 gigahertz repetitive signal that we are trying to subsample and digitize, which means that these guys are our samplers. Very high frequency input, and the output is going to be the IF low frequency, and this input here is not the output of the sampler, this is the clock of the sampler. This is the impulse train that comes into the sampler in order to do the down conversion into the IF frequency and then ultimately going to the ADC, which means that the IF coming out is actually into the board, and once we flip it over, we should be able to discover it on the other side going into the board. So we have our impulse train coming in, analog input coming in, IF going into the board. Same thing with these. These are almost identical, not quite the same, because the input dynamic range between the photodetector and the electrical input are not the same. That's why these are not identical modules. So what is this then? Well, we just talked about it. This is the impulse generator, the pulse-shaped impulse generator that goes into the two samplers. So why is this so important? Well, if you think about it, you cannot in any reasonable way send a very, very high speed impulse train, very, very short rise and fall time to this module from the mainframe. You have to generate it locally. So the trigger signal, which has very long rise and fall times, it's like a big square wave coming in at low frequency and very, very long rise and fall time, goes into this module and becomes an impulse train with exceptionally narrow width of pulses. And that's really important, because the width of this pulse will determine the ultimate bandwidth of the sampler. And I've talked about this before, and it keeps coming up over and over again. If you watch my video when I did a repair on a frequency counter, I speak there about step recovery diodes and impulse generation and what happens in the frequency domain. So it's really important for you to understand that if you want to totally understand what's going on here. So I suggest that you watch that video as well. For this purpose of right now, it suffices to say that this will generate very narrow pulses from our trigger signal. And you will have to generate two of them, because one goes to this sampler and the other one goes to other sampler. And they are willing to replicate the samplers as opposed to combining them, because they really want to have the ultimate signal integrity between these two. So now you have two IFs which can then be selected between these two IFs very easily. It's much easier to select whether you're looking at the IF of this versus the IF of that, rather than try to select between these two signals where the noise and the linearity is critical and the bandwidth is critical. That's why they would rather replicate the sampler and put up with the cost of that than to put a switch between these two analog inputs. So having said that, that's where all the magic happens. This is where all the microwave components are. Everything else is pretty self-explanatory. Everything else is just digital circuitry, analog circuitry, and we will still take it apart. And I know what you want to see, and I also want to see it. I want to take one of these guys apart and look at it under the microscope, because it should be pretty interesting to see some custom ASICs in there. I would also be interested in taking apart this optical module, because it is a very high-speed optics, and I would like to see what the photodetector looks like, most likely an indium phosphide detector there, so we'll take a look at that too. So let's go ahead and take this bad boy apart a little bit more and see what we find. Now, I should be able to. I always hate doing this on camera here, but you can see they have clips on all the ribbon cables, because they don't want these ribbons to obviously come out during operation. I see some interesting stuff on this side for sure. If I can now take this out without destroying everything. Alright, you know what? I'm gonna do this off camera. I'll be right back. So nothing all too exciting on this board. This is mostly a digital board, interface board to the actual mainframe. So there's an Altera Max FPGA on it, which, if I remember correctly, the Max series was a flash-based FPGA. So this is a flash, not an SRAM based one. If I remember correctly, you can correct me if I'm wrong on that. And there's a bunch of other components, nothing interesting, a whole bunch of power, DC power conditioning, voltage regulators, and so on. And this is some kind of firmware, obviously, that they can update as they need it. And here is the other side of that board, and here we can see, of course, everything else that I was talking about. This is the back of the impulse generator, the pulse shaping impulse generator, and this is the input to it. And this obviously is the only analog RF input that's coming from the mainframe. That was the connector I was asking you if you could guess what it is, and that goes into here. So this is our trigger signal going into this module, which becomes an impulse train, very narrow impulses for the high bandwidth that's required. So this whole module here is responsible for performing just that one task. And again, I think it might be step diode recovery based. I'm not sure. There is no information really available about this. We're kind of reverse engineering it on the fly. I have never opened this before. And these two cages that you see here are obviously the back of the sampler. So the analog IF signal, which has to have very high integrity. Remember, that signal has to reach the A to D converters, which are not in this module. They're back in the mainframe. They need to be digitized with very high resolution right here. They need to be kept the integrity so that they can be sent out right out into the DCA mainframe to be digitized. So this is filtering, perhaps. I'm sure there's some filtering component. We'll take it off and preserving and amplifying it, make sure it has good SNR before it leaves the module. So that's pretty neat. We can go ahead and continue to disassemble this stuff. And again, I'm gonna not try to do this. Oh, maybe I can do this one right here. There it is. We can separate that guy. So I'm gonna continue to take this apart, and eventually we'll be able to look at some cool stuff under the microscope. And here's a close look at one of the IAF modules, and we find underneath it exactly what we would expect. We have a pair of really ultra low noise JFET amplifiers, and this is exactly what these two components are, made by linear technology, and they have a noise of about 4 nanovolts per square root hertz at a 10 kilohertz frequency, which is pretty good. And there's some other components here which are either responsible for filtering, and I can't quite figure out exactly what's going on because I don't know what the pin interfaces are to the module which go onto the board to the other side, but either some filtering on the power supply or these are in negative feedback configuration. But either way, the purpose is very clear: ultra low noise amplification, preserving the dynamic range of the IF signal coming out. So pretty nice and clean design on that. Totally separate board, obviously designed in conjunction with the sampler, kept separate from everything else, uses a different PCB material altogether. So we can continue to take it apart further and eventually get those modules out. Well, now check this out. Here's another example of why the Keysight engineers just don't care about cost. I love that. Look at this. So this, if you remember, I talked about the pulse shaping and the sampling, and I said it's most likely a step recovery diode driver, and in fact that's exactly what it is. I didn't even notice. It says SRD driver here, which is a step recovery diode driver. And these are high power amplifiers to receive the trigger signal, amplify it to a very large amount, a very large signal peak to peak ratio, and then feeding that through this little pin into the board onto the other side to the step recovery module and creating the pulses. And on the other side, we have this little interface, which is a spring-loaded interface onto this bizarre connector on the other side of the board. So this is obviously by pressure, by putting it down and screw it in, it makes the connection to the center of that. Now remember, the frequency here is really low. It's in the kilohertz, tens of kilohertz. So it doesn't really matter. It's just a matter of preserving the integrity of the signal. It should have no added thermal and phase noise on top of it. But the purpose of this board is just driving that, but just crazy mechanical design choices in order to get the signal onto there. And you can see this is a choke inductor there, which biases the very high power transistors there. So really neat stuff. So we can continue to take it apart, and every time I take one of these things apart, I'm always amazed of how they've chosen to design it based on, you know, the maximum performance, not necessarily the cost. Obviously these are completely custom, totally unique to this particular module, so no wonder this thing costs, you know, $85,000. So let's start from the sampler module. So I've taken the cap off, the cover at the back and the front. These are glued in because they're assembled obviously by hand, one at a time. And there's a whole bunch of RF absorbers that we've seen this before, I've talked about it before, and they put these RF absorbers in various locations in the module so that because the chassis is all metallic, you don't want internal reflections and internal cavity effects and stuff to take place. So by putting these absorbers all around, you contain all the EM field within it, and then you prevent them from bouncing around the walls of the module in an unwanted way. And check it out, it's really neat. The substrate, which is most likely quartz in this case, is transparent. So whatever material they're using and whatever exotic, you know, 3.5 type technology they're using is directly on top of this quartz substrate carrier there, and everything else is gold plated. You can see various different wire bonds going from the different pins onto the main carrier there. And we'll look at this under the microscope. I just wanted to give you a global view of how it looks like, completely and utterly custom made. The input being on this side, if I'm not mistaken, I forget now, I should have marked which one was the input, but either way, one of them is the impulse train, one of them is the input coming in, and then these guys are used for biasing, and of course the IF signal coming out. And the IF signal going through this will go through the PCB and then onto the board that I just showed you, the low noise IF amplifiers. That's how the interface is made. Totally custom, just for this purpose. Pretty amazing. It's similar to, again, what I showed in one of the other videos for the frequency counter that had a step recovery diode as well built into the same module. But this is just the sampler, no step recovery in this one. And here's the optical one. So these are, again, I'm touching all these by hand because it's dead. You should never do this. You touch any of these things by hand without ESC protection, and you can be sure that they are dead. So this thing is interesting. Actually, this optical module is pretty old-fashioned. I mean, people don't build these this way anymore. You can see that the coupling between the fiber and the module itself is done through a collimator, and there's a gap here, so it actually shines through an opening on the surface of this into the module. They don't couple optics this way anymore, but this is an interesting way that I've seen this module built. Obviously, again, totally customized for this purpose, but I am curious of snapping this off, and this is not, the alignment of this is done you know, in the lab. So they would put this in, put the light in there, connect this to a signal, align this with the machine very carefully, and then they kind of weld it or glue it in place, because if you align it even by a fraction of a millimeter, then your responsivity goes down the drain. So this is why it's so important that this is done this way. This is custom, so they don't really care about the cost of testing and alignment. And here is the biasing for the photodetector from a single pin going in the chassis, of course, the other terminal. So we can go ahead and try and snap that off and look and see what it looks in there, and check a look at both of them under the microscope. I'm not going to open the step recovery diode module because you've already seen, you know, they're going to be very similar to the other one. I'm interested in seeing this and the other one under the microscope. So I take back part of what I said. I thought the collimator was built into this portion of the module, but it's not. Interestingly enough, it's built into here. Look how cool this thing is. I mean, it's just crazy how they've built this with this optical window and the lens, tiny lens that you see here, which focuses the light onto the photodetector. Unfortunately, I cannot open this. These are all hermetically sealed, and this is welded shut. I would need all my tools to tear it open, and maybe I'll leave that for a different video, because I want to show you how the coupling is done and what the photodetector looks like and how the interface of all of that looks like. Unfortunately, I can't do it. This is just you know, single mode fiber termination here. That's it. There's nothing else going on. It's just at the right angle, and the alignment is still really important, of course. So this alignment here, you know, the way it was very critical and no longer aligned, of course. But there is also further alignment requirements inside the module as well. But it looks otherwise pretty straightforward other than that. So since we're not going to take this apart, maybe we'll take a step and actually take the step recovery module open so that I can have two things to show you under the microscope. One other thing, I really want to turn this on and test it because it'd be really easy to test this. I just have to, you can connect this directly to one of the Keith Lee's source measure units, SMUs, which you've seen me review and extensively showing different things, and we can measure its responsivity. We can put light of different wavelengths in it and connect it to the oscilloscope and see what comes out with a spectrum analyzer. I don't have my lab set up yet, but I would love to try that and plug this in and test it out, but I'll save it for future. And here's the pulse shaping unit taken out itself, again completely custom module. And one thing I forgot to mention is that this component that you see here is just a junction diode used to measure the temperature of this. This is a temperature detector, and they have that captured into this little clip here, which presses against the body of this monitoring the temperature. The reason is because this is a really high power component, and if you look at it, you can see it has absolutely no DC biasing at all. So the signal coming into it has to have a tremendous amplitude. And by monitoring the temperature, they can ensure, that they adjust the input level required in order to get the optimum, response out of it and so on. That's why they need to know what the temperature of this is in order for it to work well. So now that we have it, we can take it further apart. This is where the input signal comes in through just a pretty crazy architecture, really. And going in, and then it has actually 4 outputs, if I'm not mistaken, so it most likely generates 4. I really want to test this on its own also, but I can't. Again, I don't have my lab, but we'll take it apart and see what it looks like on the inside and whether these two signals actually are present. Given that they're terminated, I'd say they're probably there, so it'd be interesting to see what's going on in there. So every time I take one of these things apart, I'm always amazed of what they have chosen to do. This is really, really interesting again. So the driving signal, the very large amplitude driving signal is, and that center pin over there. And that center pin that goes into something which I'm going to show you in a second, and then it's split into 1, 2, 3, 4 pulse-shaped impulse train that's coming out of the step recovery diode. And this is the module that is sitting in the center there. And then you can see in the center of it is where the signal comes in, and you got 4 diodes most likely sending signal in 4 directions. Really, really neat. So we're going to take a look at this under the microscope. So now we have 2 things to try. I'm very eager to see what they look like. And here we have the 50 GHz sampler directly under the microscope, and it looks very similar to the sampler that I showed in the frequency counter video. And the input signal over here, so this signal coming out from this side is the 50 GHz signal, and the signal coming from the bottom over here over this trace is the step recovery output, which are the very sharp impulses. And there's the sampler detecting module in there, which is either most likely a diode simply put there for that purpose. And you can see that it has 2 symmetric outputs, and most likely these are a differential output generated from the 2 halves of the cycles of the diode. So maybe there are 2 diodes back to back there. I'm not 100% sure because the architecture is really unknown, and there's some biasing signal coming in. Obviously all these also provide biasing at the same time to turn on this module, and then there's dynamic biasing so that it's precisely at the right point and so on, but it's pretty straightforward otherwise. And if I go ahead and zoom out a little bit, you can get a slightly better idea of what the overall module looks like. Sorry, I really need a better microscope. It's not the greatest thing in the world, but there it is. You can see the different pins. So these pins over here, you can see wire bonds and capacitors along the way. And these are the outputs that are coming in and out, and this is from this side we have the low signal from the step recovery diode coming in. And here I'm not 100% sure what is going on here. It's a very, very small component, maybe a matching network in order to ensure a good interface between the impulses coming in and the detector here. But it's again totally custom, totally non-silicon, made only for this purpose. Really neat looking, quite nice to see what's going on in there. Now if I look at the other one, which is the step recovery diode itself, which is also really cool. And this one, as we would expect to see, has the 4 outputs. So we have 4 diodes, 1, 2, 3, 4. Here's the input signal coming in, very large amplitude, hitting the step recovery diode. And then there's 1, 2, 3, and 4 outputs, which are the impulses coming from the step recovery going on to the sampler module. So really neat to take a look and see what's going on in there. I really enjoy looking at these, and I wonder if I might be able to flip this guy and see on the other side of it. Ah, there we go. Oops. Well, there it goes. That's what I'm sure I destroyed it, but that's okay. I just wanted to see what's on the other side of it. On the other side is just a bit of a PCB, the quartz material. This is also made of quartz. You can see the back of the diodes. You can clearly see the outline of the different interfaces that are making up the junctions of the step recovery diode there. So pretty neat. I hope you really enjoyed it. I do enjoy making this type of videos. I really want to test and measure these. Unfortunately, I don't have the necessary equipment to do that. And I'm going to do my Q&A next, and I'm going to announce that there's actually finally a Patreon account, so you can go and check it out, but it's not officially released yet. So if you're interested, you can always help me out to set up my lab and get everything going on. So make sure you watch the Q&A. There's a bunch of cool information I want to let you guys know about. And if you like this video, let me know. Give it a thumbs up. And yeah, I'll try to do more. There's lots and lots of stuff that's backlogged that I need to complete, but I'm looking forward to finishing it. So until next time.